In this tutorial, we will implement the Mandelbrot set in Max. Before we start patching, I will quickly go over the definition of the Mandelbrot set. So we take the following formula. C equals C squared plus C. So we take this formula and we plug in complex numbers. So the whole thing lives on the complex plane. And the idea is that we repeat this formula over and over again, and the output of one iteration becomes the input of the next iteration. If we say this is the input, C0, and then here we have the output, and then if I copy this, it will look something like this. And then next iteration would look something like this. So we plug this in. This is our first output, and the first output gets plugged in here. Second output gets plugged in here, third output, and so on. So the Mandelbrot set is then defined as the set of complex numbers C, for which this iterative process doesn't diverge. So in other words, if the values go to infinity, it's not part of the set, and if the values stay within a confined area, it's part of the set. I won't go deep into the math here, so if you want to dive deeper, I'll put some links into the description. What I'm mostly interested in is that we can generate some pretty pictures with this process. So the cool thing about this is that it's a fractal and that you could theoretically zoom in infinitely far and always discover new interesting details. So yeah, this tutorial will consist of 3 parts. In the first one, we will implement the iterative formula. In the second one, we will add zoom and position offset. And in the third one, we will apply color. Okay, starting with the first part. So as I said, we're going to use imaginary numbers, and an imaginary number always consists of 2 parts. So we have a real part and an imaginary part times I. So the imaginary part is the square root of -1 multiplied by some value. So x is the real part and y times I is the imaginary part. We're going to interpret our output or our input texture in this case as the complex plane. So on the x-axis we'll have the real part, and on the y-axis we'll have the imaginary part. And each pixel on screen will then correspond to one C input. And then we will look for each pixel if this C diverges or if it will stay in this confined area. So every pixel essentially runs its own iterations of this formula, and depending on how fast the value escapes to infinity, we will use a different color, and that's how we get this pretty output. So yeah, before we can use the formula, we need to turn it into something that we can then actually use in our code, because squaring complex numbers is a bit different. So if we're just looking at this part, so C squared, and we know that C is a complex number, we already have our complex number x plus yi here. And yeah, if we're squaring this, we can make use of the binomial expansion. So this essentially means that we have x squared plus 2xyi plus y squared I squared. So x squared plus 2yi plus I squared y squared. Doesn't look that good, but I think you'll get the idea. Okay, now we know that, oh, sorry, this bothers me. Okay, so now we know that I is the square root of -1, so squaring this turns into -1, so we can turn this whole thing into x squared plus 2xyi minus y squared. And then we can say that our real part in this case is everything that doesn't have an I. So this would be x squared plus y squared. And then our imaginary part is the rest that contains the I. So this is 2xy. And as I said, this real part will be represented on the x-axis and this imaginary part will be represented on the y-axis. So I will get rid of this and I'll take this and put it here as a reminder. Okay, I think now we can start patching. So as an input, I will use a texture with dimensions full HD. Then a jit bang object, so this will bang on every frame. We can already plug this in here. And then we can use a jit.gl.pix code box to create our code. Okay, yeah, I will start with the z value. As I said, this is our input and this is essentially each pixel on the x and on the y axis. So we can say something like z equals signed normalized coordinates. And then for now, just say out1 equals z. So now we're going from -1 to 1 on the x-axis and from -1 to 1 on the y-axis. But what I also want to do is I want to take the aspect ratio of our texture into account. So I will do something like this. So we will multiply this by a vector. And here we will say dimensions of x divided by the dimensions of y. And here we'll just say 1. So it's taking into account that this is not a square and that, yeah, if we don't do this, the whole image will be stretched. Then we can define our initial z, which is a vector in this case. So as I said, we have the real part and the imaginary part, so x and y. And then as we're iterating over this formula, so we're always taking the output and then putting it back into the input, we will need a for loop. So in order to use a for loop, I will define a maximum number of iterations, which is 500 for now. I mean, this number depends also on your system. So if you have a very strong computer, you can maybe also use bigger numbers than 500, but just take a look at your frame rate if you can handle these 500 iterations. Then we can say for I equals 0. And just to clarify, so this is the I in our for loop. This has nothing to do with our imaginary numbers here. Then we're going from 0 to the maximum number of iterations we want to do. And then we'll increment by 1. Okay. We could do something like, how will I name this? So let's maybe say we have, so I'm implementing this here now, or better, this down here. So first we're doing the real part, so we can say set real part is, so the previous set, which is just 0, 0 for now. So we're taking the x component and squaring it, so x times x. Oh, I just saw that I made a mistake here. This should be a minus. Because then we're subtracting the y component squared from this one. And then we can say that imaginary, this is 2 times x times y. So z.x times z.y. So now we have, for our next iteration, we have the real part and the imaginary part, and then we can say that z equals this vector of real part, imaginary part, and then we have to add our z to this one, because this is essentially what we're doing here. So the next z is the previous one squared, which we just did here, and then we're adding this z value here. Then we can say, okay, now we want to look at the output color. So I will create a variable, call this one color, and then we can say that we're, I mean, for now we can just say that we're adding onto this color. And as I said, so the idea is that we want to color based on how fast it goes to infinity. So in order to do this, we can say that color equals I divided by the maximum number of iterations. So this doesn't tell us anything at the moment, because this will just go from 0 to the maximum number of iterations and then divide this by the maximum number of iterations. So everything will be 1. So we need to look at, okay, how fast is this divergent? So if this is greater than 2, we can stop this loop, because we know that if numbers within this formula get greater than 2, they will go to infinity. Okay. Now, this looks more like it. But I forgot something. It's not the number itself, but the length of the number. So yeah, this is the actual thing I wanted to see. So if the length of this number, which is just like the length of the vector, so if this is bigger than 2, so you can imagine here we are at 0, 0, here we are at 1, 0, minus 1, minus 1, 1, 1. So if the length of this vector is bigger than 2, we can stop right here. Okay, coming to the second part, which is adding zoom and offset. So in order to do this, I will start with, let's call this one position, so we can move around within this one here. And in order to apply this position, we can say that we're subtracting the position from our UV positions, or from the current positions we have here. Oh, I made a mistake. It's supposed to look like this. Okay, then we can access this from the outside here. And now we can move around. In order to implement zooming, we can say, yeah, just use a parameter, call this one zoom, set it to 1 for now. I will also make some more space here. And we can apply the zooming. Was it before or after the position? No, I think I want to apply it before the position. So we can say C equals, or we can just say divide equals by our zoom. And then if we access this from the outside, yeah, the bigger the zoom, the closer we're getting. Theoretically, you could zoom in infinitely far. Beautiful. And now you can see that, okay, some parts are completely white, some parts are completely black, and some parts of the Mandelbrot set are in grayscale. So depending on how far or how fast this diverges. And we can make use of this in order to use different coloring, different shading, which is, I guess, the third part now, applying color. So we could say something like, okay, the output color equals HSL to RGB. So we're turning HSL, so hue, saturation, and lightness, into RGB values. So we could do something like, yeah, putting a new vector in here, saying that we want to control the hue by the brightness, so by the previous color value. Then we can say that, yeah, the other two can just be 0.5. And now we can see that we applied a nice color palette here. We could also do something like using an exponent here in order to change the contrast a bit. So we could say something like color equals the power function of our original color, and then we can say we can square it. And it looks something like this, or we can say that we're applying this power. What we also could do is apply an offset here. We could also use a parameter, call this color offset. And apply this down here. And then we could access this with a variable from the outside and jit.time. do I need to wrap this between 0 and 1? I'm not sure. Let's give it a try. Yeah, I do. Ooh, very trippy. Let's maybe change the speed. Yeah, look at that. What we also could say is if color is, I don't know, smaller than 0.1, it should just be black, so we can multiply color by this expression. No, it doesn't look that good. I think I'd rather get rid of this exponent here. Yeah. Look at that, very pretty. I hope this wasn't too confusing. I didn't want to go into the math that deeply. But yeah, I hope you found this useful. Thanks for watching.